Hello everyone and welcome to Tech Talk session number 16. Just a couple housekeeping things. Don't forget PDH credits. Send us an email at the end. We'll get you a PDH certificate. And also chat box. Remember to type into the chat box, ask questions. We'll get those answered at the end of the presentation. So today we are pleased to host American Superconductor, AMSC, to this week's Tech Talk session. AMSC is an American energy technology company based in Erie, Massachusetts, a leading system provider of megawatt-scale power resiliency solutions that orchestrate the rhythm and harmony of the power on the grid, and that protect and expand the capability and resiliency of our Navy's fleet. In today's session, NEPSI will be talking with Naren Reddy, Managing Director of the dvar Statcom Solutions and Planning at AMSC. We will be talking to Naren about STATCOMs. Naren is part of the AMSC business specializing in the design, the manufacture of power systems products, including static synchronous compensators, more commonly referred to as a STATCOM. AMSC also, as their name implies, produces products and solutions that involve high temperature superconductivity. The products and solutions are used by many industry sectors, including renewables, marine, utility, military, industrial, and commercial power systems. Naren, welcome to NEPSI's Tech Talk. If you could please start by introducing yourself, and from there we will get started.
Thank you, Paul. My name is Naren Reddy, and as Paul mentions, I'm responsible for AMSC's dvar Statcom business. I'm an electrical engineer by background, and I have been with AMSC since the early 2000s, helping develop products and solutions for the transmission distribution systems as well as the renewable industry. Thank you for the invitation, Paul, and happy to participate in the discussions today.
Great, and thank you for coming on the Tech Talk session. So it's going to be a great Tech Talk session. So let's start with a first question. If you could, start with explaining the basics of what a STATCOM is, and perhaps if you can touch upon what are the ratings of a STATCOM, what typical ratings do you have, voltage, VAR, current, for example. How are they connected to the power system? It's a good question. And then also touch upon the significant difference between a STATCOM and passive solutions offered by NEPSI. These would include capacitor banks and harmonic filter banks, shunt reactor banks for the absorption of reactive power or the production of reactive power. Maybe you could touch upon those things in your answer.
Sure. Let's start on some basics of what a STATCOM is and what does it do. So what is a STATCOM? STATCOM is a short form name for static compensator. Static compensator is a power electronic-based device comprised of power inverters that inject reactive current into the power system, the AC power system. And when you do that, when you are able to inject reactive current, capacitive or inductive, you have the ability to influence the system voltage or the power factor of the system at that connection point. At the most basic level, the main components of an inverter system for a STATCOM is what we have is a DC source, which is some DC capacitors that maintain the DC bus voltage reference. You have some IGBTs that are connected in certain configuration, and they are switched depending on the current or the amount of control that's needed. And then those inverters are then connected to the AC grid via a step-up transformer. This could be taking a 400 volts, 480 volts, or 335 kV range inverters up to medium voltage or even higher, depending on where the application of this STATCOM is required. So this is a basic topology of a single-phase inverter with 4 IGBTs and the DC source or the DC capacitors on the left-hand side. You have smoothing inductors and filters and the AC grid on the right-hand side. So really, it is how we control the switching of these 4 sets that really allows us to create current on the AC side. To just give you an example here, so if we switch the IGBTs 2A and 1B on while keeping the IGBTs 1A and 2B off at that time, what you're really creating is a electrical path from the DC side all the way to the AC side on the single-phase system. That in itself is what we look at as a positive current flow of the energy from the DC side to the AC side. Now, if you take that and reverse the switching of these IGBT inverters, now you have the ability to reverse the current flow. So it's really a negative current flow through the same components out there. So really, it's the switching of these IGBTs at a certain frequency, and that is at a very high frequency, usually in the 4 to 5 kilohertz range. And then basically the timing of how long the switching is maintained in the off state, or how long is it maintained on the on state, and the variability of it allows us to be able to actually create a sinusoidal output current from this device, either at 50 or 60 hertz, depending on the system that it's connected, and you end up with a nominal frequency current that is generated by the STATCOM or the inverters themselves. Taking the three-phase, two-phase, single-phase inverter topology, and then adding 2 more IGBTs in parallel basically allows us to take to a three-phase bridge for that. And of course, three-phase, the 6 IGBTs here are controlled. Of course, the complication adds up in terms of how much control that's needed for the switching. Essentially, at the end of it, what it is that you have a AC voltage that's already existing on the AC side. It may not be nominal, but there is a voltage at certain frequency. And you have the output current from the STATCOM is actually a controlled current output. And that's one of the key differences about a STATCOM, is that the output current is controlled, and you can control the phase angle of that current with respect to the AC system voltage, either 90 degrees leading or 90 degrees lagging, or you can control the magnitude of that current anywhere from 0 amps to the rated ratings of that inverter. So it is a linear control. There is no step changes or things like that. The control system can dictate exactly how much current is needed and whether it's capacitive or inductive. So really, when there is a low voltage operation, the inverter voltage is really looking at in a capacitive function. The inverter voltage would be considered higher than the AC voltage, system voltage, and the inverter current is actually pushed out through an impedance, which is usually the transformer impedance, as well as some internal impedances of the inverter system. In an inductive current requirement, if the grid voltage is higher than nominal, the STATCOM will inject current 90 degrees lagging to the voltage, and that has an effect of reducing the system voltage at the connection point, similar to how a capacitor or a reactor would do in each of these situations. So just taking the STATCOM controls, I've shown you the three-phase inverter bridge, but now kind of showing a little bit detail into how the sinusoidal pulse width modulation technique and all of these additional controls that need to go into it in order to make the system operate autonomously in a closed loop basis. One, you need to be able to maintain the internal system voltages and currents and within their design ratings. Secondly, you do have a objective that you're trying to meet on the system AC side. So you have to continuously monitor either reactive power, you have to monitor the voltages, or whatever the objective may be, as we'll talk a little later on. All that needs to be fed in, and all these control loops are operating at very high frequencies to make sure that the system overall is doing its job as designed. So that's at a very base level, taking into now, how this is converted to really a product for AMSC. Our Statcom is recognized by the name dvar Statcom, which stands for Dynamic Volt Amp Reactive Statcom Units. It is a proprietary trade name for AMSC Statcom. Statcoms provide reactive capability both leading and lagging. So in other words, a 4 megavar or 10 megavar Statcom unit essentially is designed to be able to provide up to 10 megavars capacitive or 10 megavars inductive, depending on what the requirement is. But that's the nature of the inverter. It is just essentially a control functionality that provides. dvar Statcom, in addition to some of the features that we'll talk about, it has a capability, short-term capability of 3 times its continuous rating. So essentially a 4 megavar dvar Statcom unit, right out of the box as it's designed and built, actually is capable of 12 megavar capacitive or 12 megavar inductive for up to 2 seconds. You'd note that Statcoms are, as I mentioned earlier on, dynamic devices. They're fast acting. And so really their application is to address problems that require very fast concentrated amount of VAR support. And so this is where the short-term overload really comes in handy on that. In addition to that, we'll talk a little bit in the presentation here about extending the capability of this system with hybrid systems, meaning integrating cap banks, reactors into a dvar system overall with the kind of consolidated controls. But also for renewable integration, we interface with wind farms and PV solar farms as needed, and these are all controls that have been built. Just showing some pictures here. On the far left is a master controller for the dvar system. One installation will have one master controller, and this is where the master controller looks at all of the control logic that I mentioned earlier on, or talked about earlier on. The dvar power module, this is our standard building block, 4 megavar building block Statcom. It's 4 megavar leading to 4 megavar lagging. Steady state capability, as I mentioned, 12 megavars leading and lagging a dynamic transient basis. This is a fairly standard design for us. It's about 2.5 foot by 2.5 meters by 2.5 by 2.5 cube box. On the right is a picture of an installed Statcom unit. As you can see, we step up the output of the Statcom connected to a 4 MVA transformer, as you can see, through a direct bus connect, and then stepping the output up to the medium voltage. It could be anywhere from 11 kV. You can step it up to 69 kV depending on what the customer application requires. In terms of the design and environmental requirements, the Statcom itself has been designed right out of the box to be fully operational from -40 to +50 degrees C, which takes care of a lot of our application region. We do supply these systems worldwide, so we have a lot of systems globally in very cold climates, in very hot desert areas as well. We have over 185 systems sold overall. And for specifically special weather packages, our options are available. As you can see in this picture, there's a cold weather package. If the site is going to have some snow, we can do that. If it's going close to an ocean environment, we do have stainless steel or marine paint options in terms of the enclosure, also for the transformers. One thing to note is that this Statcom is a air-cooled device, so it's got air filters in there, and those filters, as I'll talk a little later on, they do require some replacement every now and then, but it's just a very, very simple replacement procedure for that. These units can be deployed up to 1,000 meters without any derating, and above 1,000 meters of elevation, there's slight derating of the units that can be done, but we will take into consideration these calculations as to where that is going. In terms of a design life, we do recognize that this is a very common product that's going to go in utility substations. Utilities are going to own these substations and going to own some of this equipment at some point. We designed this with a 20-year design life in mind. And basically some of the recommended maintenance and replacement of this is that the DC capacitors do require some replacement over the 20-year period, once or twice maybe, depending on how it's being used. Air filters and are required to be basically checked and replaced as needed, but typically on a 6-monthly to a yearly schedule that can be done. There's a list of general, 6-monthly check that's done, which is really essentially checking on air filters and making sure there's no clogging, and making sure that the bus bars are all torqued and everything's running as usual. There's not many moving parts in it, other than the impeller fans that are at the back that are used to draw the air in and cool the inverters. You can see a picture of a single pole inverter out here. So you can see on the right hand side, that's 4 megavar PME box in front of it opened up, and 2 megavars worth of inverters basically shown for simplicity. So, Paul, I know you mentioned you wanted to look at STATCOM. Hopefully, I've given you some very basic idea about what STATCOM wise mentioned, but in trying to contrast it with regards to passive devices, compensation devices like cap banks and reactors, I'm putting this table here to kind of give you an idea on it. The STATCOM, primary thing is that the STATCOM is a dynamic device and it's very fast. In other words, it's a sub-cycle response time, and it's tunable based on application. I mean, based on our experience, we see that sometimes, you need full output of a system, maybe, 20, 30, 40 megavars, anywhere from 30, 50 millisecond time frame to maybe a second. And it really comes down to an application, comes down to what the system requirements are. As opposed to a passive compensation device, a cap bank or a reactor bank, look, both of them do provide reactive power. Reactors provide the inductive or the lagging power, reactive power. Capacitors provide the leading reactive power. But they are switched. They are in chunks. They are switched, and they're switched using conventional devices or switching devices, cap switches and all that, which typically take 6 cycles to be brought in. And then, of course, minutes. If you're doing control of these devices, it takes minutes in terms of changing power factor and all that. You really don't want to be switching these devices too fast either, because it's going to do a lot of harm or put a stress on the switching devices. As I mentioned on the product features, it's fast dynamic output that's continuously adjusted on a cycle by cycle or a millisecond basis. There is no step functional output on the STATCOM. Another key one is that the STATCOM is really an independent phase operation device. In other words, it can, based on if you're looking for a transient response, a transient might be a fault which may not be balanced. It could be highly unbalanced fault. The STATCOM, if its job is to respond to that SAG event, fault response, then it would respond in an independent phase basis, depending on what it is reading. Advanced and flexible controls. Of course, in terms of controls, I'll talk a little bit later on that. The controls are very, very similar to any synchronous machine or anything that's doing volt-var control on a continuous basis. That's the STATCOM is capable of doing. Also providing LVRT, HVRT, specific current injection type performance, and of course the short-term overload capability, which is not something that's easily available on the passive devices. But passive devices are very cost effective. I mean, no doubt about that. They're much more standard. They're regular. They've been tried, tested, and been used for a long time. They're much more reasonable, and they can be made into filters. But the neat thing is also that more and more what we're seeing is that we are using or selling STATCOM systems that are hybrid. And hybrid means that you have certain portion of the system as STATCOM, certain portion with cap banks or reactor banks. And I'll talk a little bit later on the presentation on that one. Some of the disadvantages, obviously, STATCOM is a little costlier and expensive, but for the cap banks, obviously the output is subject to the square of the remaining voltage, and you need to. There's got to be limitations in terms of how many times you can switch it in and out, but also there are ways that we can improve on that using discharge capacitors and things like that. So. Discharge reactors and all that, but I think we'll cover some of this later on. But hopefully, I've covered some of the things that you're looking for, Paul.
Yeah, no, that was great, Naren. You actually covered a lot there. I'll just maybe some key takeaways I've got on this is you talk about current source. It's really var source, right? It's a var source, and it's either inductive or capacitive. Another thing is veneer control. When we sell a metal closed cap bank at the medium voltage level, sometimes we are switching 5 megavars at a time. You're switching, and that's 5 megavars or 5,000 kvar versus what you're switching, which is a kvar or even less, and that is veneer control. Very, very small increments in kvar you're able to control across a continuous spectrum. So that's like a really big difference when you compare that to a passive metal closed cap bank or filter bank that we sell. And the other thing I think is key is we are only able to change our kvar output in increments, and then when we open we have to wait for a discharge period, and as you indicated, we can't provide fast discharge, but on a relative scale of speed we are much slower. And then finally, dynamic vars. We would classify our stuff as passive and your stuff as dynamic. So I think that's some key takeaways. And the other one that was very interesting was the fact that you can control vars on a phase-by-phase basis. And if you're looking to mitigate for transmission level faults, a lot of those are line-to-ground faults from lightning. And as such, you need to be able to correct for single-phase voltage sags or two-phase voltage sags. It's not always a three-phase sag that you're trying to correct for.
So that is. Yes, absolutely, and I think you also raise a good point in terms of the cycling. If you're looking for something that requires repetitive compensation, I mean, this is where STATCOM comes in as a product of choice, because you don't have to wait, and especially if it's fast and flicker type applications, and we'll talk a little bit later on if it comes up. But yeah, absolutely. That's for cycling. STATCOM is much better. But one important point I also wanted to kind of make here is that traditionally STATCOM technology has generally been known to be kind of more of a large transmission application device. But I think one thing that important for our viewers to understand is that now over the years we have really brought this technology down to a very much a deployable level where you have 4, 2, 4, 6, 8 that megavar range systems that can be easily configured and deployed in weak grid systems, and you don't really need to think about hundreds of megavars to be done. Yet you still get the benefit of the technology in terms of the fast response and other things that you're looking for, including program overload.
Yes. All right. So very interesting. We'll pass on to another question, so in regards to ratings, can you talk a bit about reactive power output versus system voltage? We all know that capacitor bank VAR output varies by the voltage square. As such, the VAR output drops significantly with voltage. So for example, an 80% voltage sag on a capacitor bank would result in just 64% of its VAR output. So it's a significant drop in VAR output. So can you tell us how the STATCOM responds to voltage sags, or what happens when you have an over voltage or under voltage condition?
Sure. So you bring up a good point, and as I mentioned earlier on when I started, is that a STATCOM is a controlled current device, or it's a current control device, meaning that the output of the device is actually a certain amount of current that is controlled, amps being certain magnitude as well as a certain phase angle, whether it's leading or lagging. So essentially, what happens is that the vars, or the reactive power that it has now injecting into the grid, is something that it's directly proportional to voltage. So Q equals I times V. As opposed to capacitors and reactors, which either they are just on their own, they're switched in or out, or are they utilized as part of other devices such as a static bar compensator. They are what we call impedance devices. So you really have certain voltage that you're imposing onto these devices. And like you said very correctly, that the output, the net output of these devices, the Q, is really something that's dependent or dependent on the square of the voltage. So what does that mean from in terms of effectiveness? That's how we look at it, is to effectiveness of the vars. Now, obviously, this chart I'm showing voltage versus effective output, and I'm comparing 100 megavar capacitor vars. So think of it as 100 megavar SVC that's running at a capacitive output full. And based on the voltage, and on the Y scale you have the voltage. So at 1 per unit, really that SVC will be able to give you 100 megavars net output at its terminals. But that voltage, as the voltage drops to 90%, 80, 70, like that, what you will see here is the effective output of that SVC, or those capacitive vars, is actually dropping exponentially by the square of that voltage, right? And really, when you're thinking about cap banks, or you're thinking about SVCs, dynamic devices, you're really needing them not near nominal voltage. You are needing these devices for voltages that are significantly or changing way away from nominal. So you're expecting these devices to be able to provide support at voltages that are 90% or less. But what you see is, their output drops. But this is where the studies need to come in to size. What's your deepest problem, the sag that you're trying to solve? And that should basically then dictate what is the size of the SVC. It doesn't necessarily have to be 100 megavar or 200 megavar. It'll be what it is required to bring the voltages back. So compare that with a STATCOM output on an equivalent scale, 100 megavar STATCOM. You will see that, as I mentioned, it's linear to voltage. It's directly proportional to voltage. And so at voltages low of nominal, incrementally you get more vars from the same rated device. And that's one of the reasons, actually, we believe that this technology is really picking up, and customers' applications, they're really dictating, and standards are coming out where STATCOMs are now being required. Grid codes specifically ask for STATCOMs. Another point just to note here, that you will see that the red graph here really cuts off at about 50%, which is where SVCs typically would cut off. At 50% voltage or less, thyristors are really blocked off, and they won't be operated. Typically, that's 70% or greater, but we've seen that come down in some cases. But for STATCOMs in general, you'll note that my graph is showing that we can go down to 0.2 per unit, or in some cases even lower than that. What that means is that STATCOM technology can continue to operate, continue to generate current, as long as there is some voltage available on the grid to be able to give it reference for the frequency and the phase reference that it's looking for. Other than that, it will be able to provide all that current all the way up to 1 per unit voltage, incrementally better than a static capacitor bars. So another point that I'd like to point out here, I mentioned about short-term overload, which is basically a time-based capability for the dvar, and for 2 seconds, the dvar can put out 3 times its rated current. What that means is that when you have faults or deep sags, a 4 megavar device can essentially put out up to 12 megavars. And that impact of that 12 megavars is that you're going to have a voltage rebuild, or a voltage, you're going to bring some surges down by, depending on how much current you're putting in. So this is something that's really reserved for transient applications. We don't use that for normal regulation. The continuous reactive current is something that we would use for normal regulation operations. But when we look at it, this also overload capability is something a little bit flexible for our design. 3 per unit is the maximum that we can control the system to put out. But there are certain applications that may dictate a little bit of extra current for a longer period of time, such as, let's say, a motor start application that takes 10, 15 seconds or something like that. And so we can actually control the level of overload and have it available for a longer duration. So this has been something that we've very commonly used for power quality applications as needed as well. So I just wanted to point that out. But what's interesting here is that this overload capability is something that we utilize to right-size the STATCOM solution that would be needed for an application. And for example, in this case, if it's 100 megavar, let's say studies dictate that 100 megavars SVC is required to solve the problem. And if those amount of vars solve the problem, good. But then what that shows is really this overload capability. What we do is we utilize these 2 seconds of overload capability because that's what's needed during the transient period, and that's what's utilized. And what that requires really is that you need about a 34 megavar or a third of that SVC capacity that needs to be really installed. Yet you also have the full 3 times overload, so you get the 200 megavars for 2 seconds, but then after that, you really don't need it. If you need more steady state vars, we move into what we call the hybrid time frame, and that's where we can utilize capacitor banks that you guys supply.
So it makes a lot of sense. What you're saying makes a lot of sense. Transmission level faults don't last that long. They're cleared very quickly, right? We have all kinds of relaying packages out there, pilot wire relaying, right, and stuff like that clears faults very quickly. So having that 3 times rating for, I think it was 2 seconds, maybe you said, that cuts down on the actual continuous rating that you need to purchase. So it cuts down on cost. So it's a significant item to actually specify is what is the overload rating of the STATCOM and for how long can it go?
Absolutely, and this is where it's important that when we size the requirement for a project like that, 100 megavars, that's a significant size reactive compensation device that you're going to need out at place. It's really doing the dynamic stability analysis, making sure that you model the loads and model the system appropriately, model all of the generators and all that appropriately. But if you do all of that right and you still come up with a requirement for 100 megavars, guess what? We have an opportunity to solve that with something that's much smaller in capacity and hopefully more cost effective for the customer.
Yeah, well, it's good stuff. Okay, so we'll move on. Many of us know, and we have discussed in other tech talks, the benefits of reactive compensation and power factor correction. The STATCOM, of course, offers the same common benefits associated with power factor correction, like reduced losses, voltage support, increased system capacity, et cetera, et cetera. Can you expand upon this topic and explain where the STATCOM fits in?
Sure. So if I may just start from a basic perspective of controls, and look, at the end of the day, yes, it's a current control device, but it must require customers' It must meet the customer's expectation for what the problem is and must be able to solve that. So in terms of a performance requirement, it could be to regulate voltage or regulate power factor or VAR, whatever that is. Really, the STATCOM device, as I mentioned earlier on, it is very akin to a synchronous machine, and it can control or do the same level of volt control functionality at very high frequency. So now, the dvar STATCOM, as I mentioned, hybrid use of hybrid systems, we can expand the capability if there is more of a steady state requirement along with some dynamic requirement initially. We can use cap banks and reactor banks, and what we do is use the concept of soft switching these, so that when these capacitors or reactors which are really switched in a chunky basis, when they're brought in or taken out of the system, there is no voltage change on the grid, which I'm sure you appreciate that would happen otherwise, depending on the short circuit capacity. So the dvar dynamic capability is able to absorb a lot of that shock to the system. Of course, we are able to integrate other devices. We have almost 2/3 of our applications, of 120 of these applications that are at renewable power plants. So we have developed controls that interface with power park controllers for additional vars, because these days those turbines and inverters have capabilities as well. Excuse me. Fast response for short-term capability, we've talked about using overload for those. But in addition to that, like I mentioned, that we've sold over 185 systems around the world, which has really, allowed us to look at a lot of different application needs and types. So there's been a lot of controls development to meet those requirements. There's a couple of that listed in here. There's numerous that we can do. So any new systems going out have the benefit of all of these controls being available. Just to talk about voltage control basis, I'm sure you're familiar with this. This is really a drooped voltage control approach. So there's a steady state control loop that operates, that's working, that's really looking at, let's say, a medium voltage bus or a transmission bus, and it's looking for voltage changes over a longer period of time. And it's managing this voltage on the capacitive and inductive side using some droop settings, depending on how aggressively you want to manage that voltage. And this is really, something that's operating and looking at it on a longer term. Now, while that is operating, the system is also on the lookout or waiting, let's say, looking out for any sags or surges that happen in the grid. And if any of those criteria is met for it being a surge event or a sag event, meaning that voltages are below a certain threshold or exceeded a certain threshold, the system really transitions over to that to the different control mode, and the objective is really to bring the voltages back into the blue operating range, so that from there onwards, the dvar steady state control, or there might be other devices, other equipment in the system that might take over the control and manage that as designed. So there's a lot of adjustable, all of the control features are tunable, adjustable. Of course, AMSC provides the study services as well, pretty much as a support to customers to be able to understand their application, understand the problem, because that's very, very important that we understand the problem first before we try to solve or set up a system in that way. So we provide that service as well as a planning service at AMSC. I just wanted to make a note here, show you when we talked about speed of response. This is a actual capture of a response characteristic from a STATCOM output for a sag event. As you can see, a couple of things are being shown here. One, the sag, you will see the voltages up above, that's starting off just under 1 per unit, but then there is a sag where the time is 0 cycles from fault initiation. At that point, the sag starts. As you can see, that sag is a highly unbalanced sag. the A phase voltage drops to about 70%, where the B and C phase are somewhere around 90% at that time. And then at that time, if you can look at it, the dvar system, as soon as it detected that, it injected currents on different phases with respect to how that voltage or that sag was recorded, and it responded fast, brought the voltages back up. But as soon as the sag event went back, as soon as the voltages came back to nominal, you will see that the system really ramped down very, very quickly. Almost all the event here, happened in less than about 14 cycles from fault initiation and over. But that's the kind of the design concept, and that's the application concept of a STATCOM, of how fast it comes in, solves the problem, and gets out of the way.
So that's very interesting, and when you talk about droop, these are, and response, these are terms that you often hear when you talk about generators and excitation system about generators. So it's very, you are crossing kind of into that same area that what an exciter does inside a generator, or the exciter does in a synchronous condenser. So but I'll ask this question in terms of response. Well, first, a good question is, I don't know the answer to this, but generator, when it's looking to correct voltage and you have an unbalanced voltage, what's it doing there? I don't know the answer to that, and maybe that's something that you can touch on. And then the speed. I don't know if it seems like you were correcting the voltage within a couple of cycles, that deep voltage sag. So in speed, there's a speed of response too that I wonder how your STATCOM compares to the speed of response of a generator pushing the voltage back up with its exciter.
Sure. Now, in terms of the principal function of how that droop works, it's very similar. I know that it's very similar to how the synchronous machines work, and how they control voltage or frequency droop and things like that. But in terms of exactly how a generator operates, I'm not too familiar with that. I won't be able to get into that. But I think definitely from a concept level, I think it's similar. Yeah. Now, one of the things that I would point out here, there's, like I mentioned, there's two control regimes that are in operation on this. So really, in this blue region, which is really what we call a normal voltage range, and you have your steady state droops that are in play, the speed of response in that realm is going to be actually different than what you need under a fault condition. So the speed of response, because it's something that's changing over a longer period of time, it might be a time of day, it might be, load changes over the course of the day, week, or whatever. You don't need to respond on a cycle-by-cycle basis. So there's a different set of gains and different set of parameters that are utilized for what we call the steady-state regulation rate. But when the system actually transitions or detects a fault situation, which means that there's a single phase or whatever, a big deviation in voltage that violates these regions out here for the red to come on. Now that response is super aggressive. It is in the matter of cycles, and a few cycles you need to be active. You need to get out to as max current as possible. Again, it's really objective based. What are you trying to achieve? Are you trying to protect the system from a sag, or are you trying to make sure that your voltage recovers to a certain level before a certain time expires, so that your secondary protection or secondary equipment doesn't operate, and things like that. So what you really want to do, this being such a fast-acting device, you can tune it and make it work with other things in your system, and depending on really what that application is. And I think that would be key. And this is where, going back to it, studying, understanding the problem, and making sure that the system is designed. One, you have enough capacity meaning that you have, whether it's 10 megavar or 50 megavars, what is the right number? You get to first decide that. Then you got to decide how do you use that 50 megavars. Do you use it? Anything happens, you use all 50, or you use kind of on a smaller scale basis.
Okay. So we're switched topics, and we're asked about harmonics. When I look at the topology, actually early on, you're showing topology. It does have that drive look to it almost. So is a solid state device? Does the Statcom produce harmonics? And if they do, what level of harmonics does the Statcom produce? What can you say about that?
Good question. So the STATCOMs and power quality. I mean, there are different ways that we define power quality. I mean, flicker as well as harmonics and things like that. And I know NEPSI gets into the harmonics part of the grid in terms of providing filter banks and things like that. But you're right. From a basic STATCOM fundamental level, the STATCOMs, they do generate harmonic because, as I mentioned earlier on, that there is switching of these IGBTs that are involved at a very high frequency at 4.5 kilohertz per inverter, or at an inverter level. But then those are, that's a pretty high frequency. But then there are also techniques that we use internally because we don't have a single inverter, we have multiple inverters. And so effectively at a system level or at a many inverters, there are ways that we can actually increase that effective switching frequency much higher. Now having said that, those harmonics and all that are really managed or contained within the STATCOM unit. The dvar STATCOM, by design, we want to make sure, and it's been designed such that the output current, the fundamental current, frequency current that we get out, the harmonics content of that current on the other side of the transformer, we want to make sure does not violate the IEEE 519 guidelines. And so that's something that we design right out of the gate as a standard. But for every project, we do look at in terms of how many units are going, what's the background impedance for background harmonic, is there any capacitor banks or other devices that are used that are going to potentially change the harmonic impedance of the grid. Now, I'll make a point here that the STATCOM device, the inverters do not influence the harmonic impedance, so they won't be able to change, similar to how a cap bank does. It very easily could create a resonance, at very critical 5th, 7th range, but a STATCOM inverter does not change the harmonic impedance, so it doesn't affect from that perspective. But it does if there's plenty of this, plus there are cap banks as well as other harmonic sources in the grid. Let's say at a renewable plant you have inverters out there from the turbine inverters that may have certain harmonic characteristics. Now they may be low, but if there are many of these, you have to look at the overall picture and make sure that all of that is taken into account. A study would be necessary in that way. And of course, if you have cap banks, as part of the installation, they can always be detuned. And I know you guys provide those cap bank or harmonic filters that you can, you supply that as well. So just as an example, I wanted to show you this. This is a wind farm installation that is actually unique from that perspective, that there are a couple of different things. It is in a very high harmonic rich environment. It is in a very weak part of the grid. But in this installation, AMSC dvar, as well as 4 capacitor banks, had to be installed, and not only to provide reactive power, but also those filter banks actually ended up being pretty kind of significant harmonic filters at the bank, and obviously they are switched in and out under certain conditions. So this particular installation, as you can see, it's a wind farm. Remote connection, so in other words, a remote POI, point of interconnection, is out there. But the dvar system is actually controlling 16 megavar of dvar units, and then 4 capacitor banks, 410 megavar capacitor banks that are really, harmonic filters. One other thing that's not shown on this, but this particular wind farm, because it was in a very weak part of the grid, had synchronous condensers as well, so which you talked about as them being there as well, doing certain amount of voltage control and providing inertia to the grid. But the dvar system is the master controller for the plant, and it controls the dvar, the cap banks, but it also is leveraging and using those turbine vars as needed as well. And so in terms of, it can be easily done. My point here is that these are things that we've really gone through and done that. In this picture, you can see that same wind farm. You have a synchronous condenser that's installed, 2 STATCOM units, and on the right-hand side, you will see the kind of open air cap banks, but more filter banks. So you'll see the resistor units that are on those insulator posts out there. So from a harmonic standpoint, it is really something that's manageable, something that we can do. It's just a matter of understanding what the overall application, what the overall background needs are.
Yeah, so my experience is just about every renewables project, there is some type of harmonic study done, and your STATCOM is just putting out very low level harmonic currents. I would refer people to our Tech Talk session 1, where we talk about active front end drives, which are also like another low end, very low harmonic output. And really in that Tech Talk we talk about resonance, and if you got resonance, you got issues, and that's generally the case even in renewable plants. If you got resonance, you got issues. It's not the fault of the low harmonic producing device, in this case the STATCOM, but it's something that you have to look out for and account for, and so it's good to know that it's low harmonic output. So we're talking about something else that's always kind of intrigued me a little bit, is that we sell capacitor banks into the renewable power plants, and sometimes filters, but most of the time capacitor banks. And some of the renewable power plants get capacitor banks, and some get STATCOMs, but some do not get STATCOMs. Can you just touch upon a little bit why some renewable plants get STATCOMs and why others do not? What's the difference between these systems, and why one might get them and another will not?
Sure. So renewable plant integration. I mean, renewables is something that's going to be here and for a long time, and these are going to show something that's going to shape the future of the power system overall in here. And there are challenges of renewable plant integration, as I can show here. As I'm showing here. The main factors here is the resource variability. I mean, if it's a wind plant or a solar plant, obviously the amount of the resource in the wind or the solar, cloud cover, things like that, the power which is directly affects the power output of these devices can be. I mean, there's been a lot of improvements in forecasting and things like that has manages those things, but then still the plant itself has to react to that. So it does that variability does present operator challenges because from a grid operator or a utility perspective, a renewable plant is really considered as just any other power plant. And in terms of comparing to a synchronous thermal power plant, behavior is expected to be the same, because the grid or the consumers are relying on that power to be provided. Obviously, these renewable plants are not going in the ideal, may not be going into the strongest parts of the grid. And so the weak grid conditions could apply. The impact of the renewable variable generation at a certain part of the grid might be more pronounced than other places. And so how much of renewable energy are we putting into the grid at a point really affects, how the grid would react, whether that amount of power can be evacuated or not. And also now you add on to that different technologies, right? You have, when we say wind farms, I mean, there are different types of wind turbines that can be used. Those wind turbines have different levels of capability in terms of control, in terms of a low voltage ride through, high voltage ride through, in terms of ability to support the grid if needed. And sometimes they may have the capability, but as you know, that wind farms are spread over hundreds of acres of land or distances, long distances of cables used to bring that power to a central point. Can you use all of that capability at the turbines to address a grid condition? That may not be possible. So taking all of that into account, typically what we end up with is what we call a grid code. And different regions, different countries, different ISOs have different grid codes that they require these wind plants to basically meet in terms of performance, whether it's a dynamic performance in terms of ability to handle high voltage right through, high voltages in the system, low voltages in the system, and if there are additional requirements for these wind plants to support the grid as well, because at some point, these are to be considered as normal power plants if they have to be relied upon. So grid codes are defined, and as you can see, grid codes really clearly specify what performance is required. So the more renewables that are coming in, Paul, what we notice is that there's more expectation of improved performance from these renewable plants, which means that their expectation to be more dynamic in nature, their expectation to be more supportive of the grid conditions, meaning that you should be able to act as a generator, as a single point generator in terms of doing that. Manage the voltage so that there is no other device in the system that would be needed. But then also ability to make sure that you are able to show them, demonstrate to them that these features are to be met as well. Now, whether that part is met or not is really a question on the developers with regards to what size wind farm is being done, what turbines are being selected, where is this being installed, what is the business case for them to do that. And so what we end up doing is actually helping developers understand that. And when we know that there's a wind farm going in a certain part of the grid at certain region, we can help them look at the grid code, look at the turbine capability, review the performance requirements, and see whether as an overall plant does it meet all of the requirements. Now, if the turbine capability is sufficient, or turbines have all of the dynamic capability that they need, and the speed of response capability that they need. Don't forget, these are turbines that are spread over, as I mentioned, many miles apart. But if you want to get all of the response at the same time and do that, that can be challenging in a lot of respects. So all that needs to be modeled and understood about where the gaps might be in terms of the final connection point performance. And if there are certainly gaps left, and this is where the dvar system, which we install really right at the point of connection, typically at the substation collector bus, where all of that power is stepped up to the transmission point of interconnection. That's really the ideal location to fill in any gaps in terms of the performance of the wind plant overall. And that's what helps us actually configure and sell a lot of this, because the dvar can, at that point, really take on the role of a master controller for the wind plant, while the turbines kind of are focused on the megawatt generation and making sure that they are optimized to put out as much megawatt as the wind is blowing and can be harnessed. The dvar system would take care of all of the balance of plant control capability in terms of reactive power, voltage management, grid support functionality, right at the substation level. And of course, I mean, depending on what sort of gaps are there in terms of the reactive capability, there might be steady-state power factor requirements. And this is where shunt capacitor banks, like the ones that you would supply and we've supplied together with NEPSI, in that, and that comes in, and that is there for the steady-state compensation. The dvar takes on the role of doing the faster regulation and faster mitigation. That's all. And one of the key applications that we see, as I mentioned, that we have about 123 systems that we have sold worldwide, supporting about 12 gigawatts of wind generation. A lot of these systems, the dvar units, because they are able to operate all the way down to 20% remaining voltage, it really helps providing the low voltage right through, as well as in some cases high voltage right through support for some of these very strict grid interconnections, and that's why I wanted to show the difference in why the STATCOMs are really part of the grid codes these days. If you look at anywhere around the world, STATCOMs is the product of choice for providing that additional voltage regulation.
All right, great, thank you. So we're gonna shift away from renewables a little bit, and we're going to talk about a project that actually many projects that we worked on at this point, where it's a chip manufacturing plant or a critical process type facility where voltage is critical. And anybody who's been involved with chip manufacturing knows that if you have a deviation voltage, it can wreck the batch, and there's a significant loss in product. And so chip manufacturers in particular, but other process facilities want sometimes perfect voltage. And we have worked on some projects together, and we had supplied capacitor banks or filter banks actually into those projects, and you have supplied, AMSC has supplied STATCOMs in there to support voltage sag and do voltage sag ride through. So maybe you could talk a little bit about how that system works, how we accomplish voltage sag ride through using the STATCOM system.
Sure. So in the sag protection realm, really, as you mentioned, I mean, this is protecting a critical facility or a process of the critical facility from external sags, and we're talking about sags that are happening out on the grid, through lightning or just faults in the system, single phase, two phase, or however three phase. But the facility itself has some critical processes, equipment, tools that may be very, very sensitive to momentary sags, and those sags or disturbances that happen out on the transmission system, they permeate themselves right into the facility. And typically these tools or critical facilities kind of go by some of these recommendations or sag thresholds that they should live with, such as the ITI curve or semi-F47. This kind of allows them some room in terms of ability to ride through some of these sags. But then, as you can see in this particular example, so as you can see in this facility, I mean, this is basically a record of all of the sags that this particular facility experienced, and it kind of shows you that there are significant number of sags that are outside of what would be considered acceptable for the tools to ride through. So that means the tools in this particular facility are being affected, and the intent really would be to provide sag protection or rebuild very, very quickly, so that these sags do not fall out of these thresholds, and the amount of damage to the or downtime to the facility is minimized. There are certain instances that we may is unavoidable. For example, you do have two of those events that are sitting at 0% voltage, which are basically reflecting either a very close-in fault or a outage of the system for a momentary outage. It's difficult to raise a voltage that's zero. So barring those ones, I guess the objective of the system would be to improve on the ones that are outside of the required band. So in this concept, what we do is we have what we call a PQIVR, Power Quality Industrial Voltage Restorer, which utilizes our STATCOM system, or the dvar STATCOM units, as well as NEPSI's cap banks in that. And it's really to provide what we call a facility level sag protection. very fast. It's a cycle and a half to 5 cycle kind of a response time. You got to get in there quick. You got to detect it quick. You got to solve the problem, and you have to make sure that you are not causing a problem at the end of the sag as well. So really, it's leveraging the impedance of the grid, as well as, if necessary, what we do is we influence that impedance of the grid to make the system more cost-effective or effective rebuild, while we keep the cost of the system down, without making sure that we are not impacting the customer's operations, or their load, or their tools must not be impacted. So there's a fair bit of work that goes into this, but in essence, what we do is design systems to provide rebuild of voltage, maybe down to, for example, in this case, voltages down to 30%, rebuild them up by 65%. So bring them up to normal operating level, and then also make sure that the system overall is managing all of the operations downstream of this installation, meaning that whatever customers' large facilities, motors, and things like that are operating, they're not impacted in there. And also, key thing is that really the system is something that remains on standby. So we want to make sure that there's low electrical losses, system standby, with doing nothing and only waiting for a sag. So in essence, the PQI-VR system main components, as you can see, you have a utility transmission system, step-down voltage to the local distribution. On the right-hand side, you have the protected loads. Now, in the middle is a kind of a outline of what key components that are being used. As I mentioned, that in some cases we would use a reactor, a series reactor, to kind of adjust the short circuit capacity a little bit, make the system more effective. We have the STATCOM units that are really the heart of what provides voltage rebuild. And of course, some power factor correction cap banks. These are required, especially if we are using shunt series reactors here to impact the fault power. These power factor correction cap banks become very necessary. Now, these systems, they're really load dependent, as in how much load they are protecting. Typically, this is a medium voltage installation, so you'd be protecting facility-wide load way, and the size of some of these systems for us has gone up as high as about 160, 170 megavars capability, because this is really a very crucial part of the business for the facility that's been protected. So just to kind of give you an idea of some of the components, and I wanted to show you the picture to give you and the viewers a little bit of idea of these systems. We have over a dozen systems installed, and so that's the current limiting reactors. So this is air core current limiting reactors that are actually used in series to be able to switch in and bypass those, and ability for maintenance and for protection purposes. We do have some switches installed, and this can be an outdoor kind of a lineup. Now, this is really a substation-based solution. So dvar STATCOM, whether it's used in an industrial facility or it is used in a utility grid or whatever, this is a really substation-based outdoor system. We don't need a building and all that for the STATCOM units. Likewise, what we do is we use that for all of the other components as well, such that they don't go in the building as well. So this is a picture of the dvar STATCOM units. You're seeing one unit, but typically that could be as high as 10, 12, 4 megavar units at a single location. And of course, a lineup of power factor correction cap banks. And this is not a one-step cap bank. There has to be usually multiple steps involved. But also, I'm sure you'll be able to talk to that, but a lot of these installations that you have, they're all harmonic filters. So these are something that, while we are addressing power factor of the facility to keep the voltages high, but also at the same time, you are helping mitigate the harmonic impacts of the customer as well. So this is giving you an idea. So the problem I showed you earlier on of what problem we are solving. We are trying to do a data gathering to understand what is the level of problem in sags, how deep are those sags, how long do they last, and if we did solve, how many of those can we address for the customer. But really the solution for us, the objective for us, is to actually move this into this region. So basically, as you can see, this is what the problem was, and the solution is to be able to kind of bring those sags raise the voltage sufficiently and fast enough so that you are able to let the system ride through that fault. And just basically kind of showing, I mean, there's a lot of detailed analysis, design work that goes in, including some PSCAD type analysis, EMTDC analysis to validate the sizing as well as validate the ratings of the components and things like that. And one of the things that I wanted to point out to you is, in this particular case, for example, how long it takes for the dvar system to ramp up its current from almost zero here to full rated current, or 95 or full rated, and to be able to kind of to go in there and maintain that current at the required levels, without any instability. And that's shown by this simulation, where these simulations, by the way, use the component level simulation and code and algorithms in there. So what you're really getting in the simulations is how the device would operate in the field as well. That's something true with all of our models that we are available from AMSC as well.
Voltage sags caused by external upstream remote transmission distribution faults is one major power quality concern. Let's talk about voltage sags and flicker caused by dynamic loads within the plant. So things that are happening in the plant, motor starting, welders, and things like that. This might be large motor starters across the line or other dynamic loads that might be found like in the steel industry, rolling mills, arc furnaces, or in the automotive industry, the welders. If you could talk about how the STATCOM can help with these problems.
Yeah, actually that is an important point. I mean, flicker, not necessarily it's the grid that's causing all of that problem all the time. I mean, you have industrial facilities, you have industrial small, medium, large industrial facilities that could be actually causing flicker back into or causing disturbances for the grid and other customers as well. They might be causing a lot of harm to their own operations as well in some cases. So absolutely. So as I mentioned, the dvar systems are dvar STATCOM systems are configurable. They can be sized anywhere from 2 megavars to tens of megavars in terms of capacity, and so they're very deployable for small applications as well. A classic example that I'm going to talk about here is a dredge flicker mitigation. As you can see in this graph, this is a graph of the operation of the hoist operation of that, and there's significant amount. There's almost about 2 kiloamps of current draw from the hoist motors out there that operate frequently, as every time that it's done. Not only that when the hoist is operated, but of course during the process time as well. There's a lot of variations in that load. But when we studied this thing, we wanted to identify what the boundary level voltage impact was, and whether it's the impact to the grid, or is it impact on the factory, and ability to help the facility as well to make sure that it operates. So as you can see here, a kind of a simple analysis in terms of the motor start application for this shows that the local facility connection point voltage drops by about close to 6% during one of these hoist operations, and the same event really results in the the voltage at the motor terminals dropping by over 12%. And that's significant. Now, every time that it operates, that's the amount of level of flicker or level of voltage changes, variations that is happening on that grid. So in this case, the utility worked with us, came to us and put us in touch with the customer, and we worked with them, looked at various different options. And here's an example of how we used a small 2 megavar rated device, which is really, very, very adequate for the size of the load in this particular case. Allowed us, by just putting that dvar, connecting it to the medium voltage bus, allowed us to improve that flicker from closer to 6% at the connection point to less than 0.5%. And that, in essence, basically allowed also about more than 6% increase, almost a 6% improvement in the voltage at the inside the facility or the motor terminals. So this 2 megawatt dvar, we installed that. It is a small device, as I mentioned. It's a configurable device, and now in terms of a connection arrangement for that, so this is a one-line diagram of what the facility service is. You have 1247 kV utility supply, and then a small short cable, the step-down transformer, and then you have these motors and variable frequency drives. Some of these motors are operated through VFDs as well. In terms of the dvar connection for this, as I mentioned, that the dvar unit is a 480 volt output. We utilize a step-up transformer to connect it to medium voltage, and in this case, it's a 1247 kV primary transformer. Because it's a 2 MVA requirement, it's just basically a 2 MVA transformer is purchased for that steady state. The dvar is a 2 MVA. I've shown you pictures of a 4 MVA dvar as a building block. We would use the same building block, same enclosure and everything, except the amount of inverters inside it is actually half. So it's half populated. And some customers choose to actually upgrade their system should they want to do that later on. That's an option for them as well. So 2 megawatt dvar connected to a 2 MVA Statcom step-up transformer, master control enclosure, which is basically installed. Now, in this case, we monitor the supply side currents. We look at the load side currents. We look at the 1247 voltage, basically because we want to make sure that we are addressing flicker or we are addressing voltage, depending on what sort of control mode is utilized for that. All of this signal is taken in, fed into the master controller. Also, we get a signal from the hoist operation, basically telling us or giving us indication as to when they're doing that. It kind of helps us to fine-tune the problem a little bit more and make sure that the system is more effective as and when the hoists are operating. And that master controller then basically controls how the dvar system needs to inject current, how fast, how frequent, at what current level. All of that is kind of operated or dictated by the algorithms in the master controller. So typically, AMSC scope of supply would be the Statcom unit, the transformer, master controller, and we'd work with the customer whether we need to install it or they have a balance of plant installer who can do that. Beyond the Statcom unit, beyond the transformer unit that's supplied, it's really a utility grade installation, integrated in terms of any other equipment, in terms of protection equipment, control or any of the standards in terms of that needs to be employed. It's really the local utilities and the local requirements that would prevail for those. So once the system was installed, this is an actual system that's been installed. So here's a recording of the dvar system current and the voltage that it is actually monitoring at 1247. So in this first phase here, so the upper graph is the dvar Statcom current output, and here is the voltage. The green, this is 1 per unit. The dark green line is 1.01 and 0.199, so 1% on either side grids. As you can see, when the system is in standard voltage regulation, the dvar system is really responding based on how the voltage is moving, depending on how the operations is going. It's a lot more relaxed, and the voltage variations, while they are still maintained within the requirements of the dvar system between 0.98 and 1.02, kind of a range that it's required to be maintained. It's doing that, but it's still relaxed a fair bit. But when the system is actually, you'll note that it's switched over to a dvar flicker mitigation mode, meaning flicker mitigation is maintained. Well, now it's looking for actual flicker and trying to improve that. You will see that the profile of current output really changes based on what's happening, based on the currents of the load of the motors and all that. And if you look at the voltage, it's much, much tighter, cleaner voltage in terms of flicker. So that's kind of giving you a real example of how the dvar can be utilized. Okay, so this is actually a slide just showing some pictures of the installation. As I mentioned, that this is a 2 megavar dvar unit, but as you can see, the picture, the size of the Statcom is really the same box as for the 4 MVAR. It's really half of the box is inverters in it, just sized for the application. But the transformer that we selected for that is a 2 MVA, as you can see on the bottom right picture. So this just gives a couple of different angles in terms of the installation requirement. There's a concrete pad that's needed for it, and both the dvar and the transformer just sit on the concrete pad. That the throat connection allows it to sit at the same height on that. In this particular installation, we also had to supply a control building. Obviously, this was a remote installation at a facility where there was no control buildings and things. So we provided that to house our master controller, plus the auxiliary supplies and things like that. And that's certainly something that we can manage depending on the requirements of the customer on that. So Paul, with that, this hopefully gives you a good idea of small industrial installations to address flicker. And as I mentioned, the systems are scalable anywhere from 2 megavars to tens or more of capability as needed.
And you of course have that overload capability to actually push those limits even further, right?
That is correct.
Yeah. All right, so let's get into a little bit about cost. It's the big question that everybody always asks, and from our perspective, and you're in the same area, we get customers that come to us and they really don't want to spend money. Even when we have customers that we know might have resonance issues, we recommend filters which have higher costs, and a lot of times they elect to not purchase those filters and actually go forward at risk. So maybe you could just talk a little bit about Statcom costs and what types of projects you're going to say to the customers you should be really thinking about the Statcom system.
Sure. So if I can advance the slide. So that's agreed. Cost is a major factor in the decision, and any solution per se. And as you can see, depending on the customer, depending on the application, depending on the ability or the appetite for the customer to solve the problem, what's important for us to understand here is really the application. As we mentioned earlier on, both of these devices, a Statcom unit as well as a passive capacitor bank, filter bank, or a reactor bank, they all provide reactive power. The question is they have their own place in terms of the value proposition they bring to the customer, in terms of speed of response, in terms of capability, in terms of how fast they are switched, and in terms of really how the best they can be used. So I go back always to what is the application. If we get to understand the application and really then know that that's what the customer wants to be addressed, solved, and obviously there'll be a budget that needs to be met. All those things have to be managed, and of course we have to understand that they're met. It's the problem, dynamic problem, as we discussed, flicker mitigation or low voltage ride through, high voltage ride through, then obviously a capacitor bank or a passive device will not be able to solve that problem. cannot be used. Really cost would be then what's the right size STATCOM that is needed for that. But if it's not dynamic, if it's more of a steady state long-term requirement, if it's just to switch it in and no repetitive switchings are required, passive solutions are just fine and cost effective. And in that case, a STATCOM does not make sense. There's no need to spend more money on that. But in some cases where you may have need for capacitive as well as inductive capability at one point, and the application would be such that you need both. Well, now you may want to consider STATCOM, because if you go putting in a couple of cap banks plus a couple of reactors, and if you consider all the switches, the footprint, and all of that thing that goes with installing that, maybe just one STATCOM unit would be able to handle both of that. So there are some ways that you could look at both of them. From a general cost standpoint, STATCOM systems, you can expect the systems to be anywhere from 3 to 6 times higher in cost to an equivalent passive device. But it really comes down to the functionality. It really comes down to the value proposition. What does it bring to the customer? How does it improve their solution, right?
So this kind of brings up a key last point for us is hybrid solutions. There's ways to have these systems work together to leverage the economies of both, and maybe you can just touch on that for a moment.
Absolutely, and a hybrid solution is really the way that we've observed, and this is how we've actually presented to our customers, and it is very, very popular. Is ability to fully define the characteristics of what the problem is, making sure that the dynamic portion of the solution overall meets the dynamic performance expectation of the system, but then for the longer term steady state requirements, we use the passive devices. For example, a 50 megavar. Let's say we do the analysis and we come up and it's a 50 megavar of dynamic compensation is needed, but not all of it is needed for long periods of time. Well, the way that we would approach that is to put in a STATCOM that's about a third of that rating. So a 16 megavar or 18 megavar, in that range of a STATCOM, would really meet the customer's 2-second or the full dynamic requirement, sag mitigation or transient response, all of that current within that time frame, solve all the dynamic problem, bring the voltages to normal ranges. But once the voltages are in the normal ranges, then we would actually use those cap banks that are used, or reactors as it may be. But in this example, we are showing a 16 megavar dvar with 2 by 17 megavar cap banks, really providing a 50 megavar dynamically variable system, but also providing a 50 megavar instantaneously variable system as well. And so it meets both aspects. One, it meets the customer's performance requirement. Secondly, it's now the STATCOM, which is really the expensive part of it, is a third of the overall solution. Instead of a 50 megavar STATCOM, you're putting in only a 16 megavar STATCOM. If you look at the cost savings, it actually flows down into the installation, the substation, all the way through. You will see the benefit of doing that. And the other neat point about hybrid solutions that we do is the capacitor or the passive device sizes are selected in such a way that we could use the dvar to provide the soft switching capability. So really, from a performance standpoint, it is a fully dynamically variable 50 megavar capacity at the point of connection. But internally, you are leveraging different technologies to do that. Now, I just wanted to show you in an example, what does this soft switching capability really mean? You know that when you switch in a single step cap bank, you'll get a step change in voltage. Let's say you switch it in, you'll get a certain rise in the voltage. But when we do soft switching of these capacitor banks, you will note this is an actual capture of the voltages during a switching out of a capacitor bank. switching in of a capacitor bank, sorry, you will see that when the cap bank is switched in, there are some momentary transients. Now, these are some transients that's based on the inrush current and the system impedances at a high frequency that is kept that's there. That the dvar does not address that. But if you look at it a cycle or two later, after the cap bank has all three phases have been switched in, you will see that the voltage magnitude post bringing in the capacitor bank is almost the same as the one before the cap was switched in. Now, how that works is that the dvar, basically being a dynamic device, it regulates its dynamic output in such a way that it offsets the impact of the capacitor bank either coming in or going out. And so this is where a hybrid solution with this functionality really gives you a performance of a fully dynamic system, but in a much more cost-effective way.
Yeah, so maybe this is very interesting. Maybe you can go back to the previous slide with that shows that slide 58, and it's interesting. So what you're saying here is that we can have plus 82 megavars dynamic and minus 48 megavars inductive. So 82 megavars capacitive, 48 megavars inductive, basically for the price of a two-stage 17 megavar capacitor bank and 16 megavars of STATCOMs, the dvar systems, the STATCOM systems. So that's an amazing cost savings and a significant amount of megavars that you can dynamically switch.
Absolutely. And one of the other points that I would make is that, as you mentioned earlier on, that you also provide fast discharge capability in this, cap banks, which may allow it to be, switched quickly if needed. The question when switching in capacitor banks or switching in any var is you're responding to an event or responding to a requirement in the grid. Question is, does that requirement going to be sustained, or is that something that's short term and then you needed those vars but you don't need it? Is it too variable enough? Now, if you have these capacitor banks multi-step, but also have some fast discharge capability embedded in them, now you're making the system really flexible from that perspective.
Yeah. So I'll bring up a couple points for fast discharge. We have supplied many systems that we can fast discharge a capacitor bank. Typically, you have to wait 5 minutes, but we have installed fast discharge systems that make those capacitors available within a couple seconds. And so this is something that would interest you in this area where you're doing hybrid systems.
Absolutely.
Yeah. And then on the next slide, 59, you show a transient. So especially at the 38 kV level, but even at the 15 kV level, the transients can be eliminated with the switching device, either a pre-insertion resistor in the switching device or synchronous closing using zero voltage closing. So in that situation, you would be transient free, and that would be a perfect waveform then.
Absolutely, yes.
Yeah.
Yes, there are different ways of addressing that, and you guys are experts on the right devices and the right to go to do that. Yeah.
Okay, so Noreen, that's it. We're gonna switch over to questions now. We're gonna go to a question screen. We'll pull up the chat box and we'll go through what the questions are. We'll come back on in just a minute to answer those questions for all the viewers.
Sure.
Okay, so I got the questions in the chat box up. I'm going to read the questions off, and Noreen will answer the questions, and maybe perhaps I will interject where I can. So the first question came in from Wesley a while back, actually. Sorry for the wait. It is principally principally the inductance of the inverter transformer that smooths the steps into the waves. I think they're asking about, does the inverter transformer smooth the waveform, I think is the question. Is that where the principal inductance is coming from?
Not really. I mean, we do have internal to the inverters, we do have smoothing, like I said, filters or smoothing inductors in there in front of each of the inverters. I mean, that's kind of designed into the Statcom unit itself. But then, of course, the design of the Statcom transformer that used to step up to the medium voltage, that is something that impedance of that is taken into account in terms of the overall performance of the unit. I mean, that's an inherent part of the unit as well. So.
Okay, great. So next question came in from Kyle, and Kyle asked, can the dvar system be used simultaneously to compensate reactive power and harmonic currents similar to an active filter system?
The dvar Statcom, the configuration that I've shared and shown with you guys in the presentation today, is not designed for active harmonic filtering, but it's the primary design of the inverters with regards to the components and the control system. Everything is geared towards primarily doing the reactive compensation part of it. Now, of course, if harmonic filtering is important, and it depends on what's the most cost-effective way of addressing that. I mean, typically we find that passive filters, help and a very cost-effective way of addressing harmonics. You let the more costly or really Statcom units, which are generating heat and all that, the losses in those are, when they're operating is higher. So you'd want to the extent possible, to make it cost effective over the lifetime of a project, to do filtering with passive filters as much as possible. Okay,
great. Next question came in from Christiane. The question is, I have seen Statcoms operating in the grid as voltage control units. Those devices are usually owned by the transmission companies. Which other industries use this technology on a regular basis?
Yeah, and as I mentioned during the presentation too, I mean, Statcoms, as we see, this has primarily been considered as transmission devices, large and beyond the realm of average users out there. But I think what we've done over the years is really brought this technology down to a point where small modular units are available, the technology is available, the concept is available, Paul.
Yes.
Paul, I'm getting some static from you guys. So.
Okay, sorry.
So it's the ability to bring this concept of Statcom, the technology, down to small units, as I showed you, application for 2 megavar, 4 megavar, 10 megavar in that range, that allows it to be used at industrial facilities, small industrial plants, as a classic example that I showed earlier on. Also at industrial facilities, at critical load facilities, like semiconductor manufacturing facility example that we talked about earlier on as well. So yeah, it's gone beyond just transmission owners using this. This is really modular, configurable units are available. The whole concept, the controls are all available at lower voltages, lower capacities as well.
Okay. Okay, so nowadays...
Mention also on that, sorry Paul, additional note on that is, of course, any industry that has voltage variability issues, management of that, for example, mines, that's an few. We have installations in Australia, Canada, that have mines where they use dvar system for managing dynamic voltage support for the grid, as well as for the mine in terms of the large ball and sag mill motors that would operate. So these are systems are there to provide the dynamic support on that. So that's certainly an application that fits in very well with these modular systems.
Okay, great, thank you. So nowadays, grid stabilization for wind projects is typically achieved via converters installed within the wind turbine itself. Does this built-in feature of the wind turbine converter eliminate the requirement for a STATCOM within the wind farm?
That's a good question, and agreed that the wind turbine converter capability has certainly improved in terms of, and the sizes of these wind turbines have increased to a point. But I think, as I mentioned in the presentation, it's very important to do a study of the complete wind farm with the turbine capabilities and all that modeled as close as possible to what's going to be installed, to be able to really understand whether the individual capability that is installed at the turbine level, which be probably 600 volt, 1 kV in that range, but between that and the grid point of interconnection at the high voltage side, where the utilities or the grid operator is really interested in the performance, whether that capability can translate to all of the requirements at the HV side, that is challenging because of the distance, the impedances, all that's involved, the limitations of high voltage right through high voltage and low voltage operational capability of those converters. So does it eliminate? We haven't seen it eliminated. What we have seen is that there has been some reduction in that requirements, but then certainly there's gaps that have to be met at the point of interconnection, which, even though that capability might be available individually, but it's not able to be harnessed at the point of interconnection.
Okay, great. So back to another question from Christiane. Do the transformers that connect STATCOMs to the grid require special isolation in order to account for the high VDT characteristics of an inverter output voltage?
We do specify the grid STATCOM transformers specifically based on the characteristics of the output of the dvar system, inverter output. Also, in terms of making it ensure that it meets the harmonic requirement, but also all of the voltage ranges and things like that have to be taken into account. And we work with the transformer manufacturers to make sure that the step-up transformers are fully compliant with regards to how the device would be used, knowing and understanding that there will be primarily reactive current that should be used for. So.
Okay, so there's a question in regards to the DC capacitor, and that came in from Mustafa. What is the typical life of the DC link capacitor used within the STATCOM, and also the typical lifetime of the whole device? And maybe I will ask a question: what type of capacitor is it that's used in the DC link? If you know what that is.
Yeah, there's different forms available. The ones that we have kind of used mostly, or the dvar STATCOM configuration uses, are electrolytic type caps at the moment, and these caps typically have a life of about somewhere anywhere from about 7 to 10, 11 years time frame, depending on the use, the cycling, and how the device has been maintained over the years. We've seen, one of our first STATCOM systems we've installed was in 2001, and as I mentioned, we've sold more than 185 systems overall. So now that we have quite a bit of fleet out there that we have been able to manage, track, and understand the life, the cycle of all of these devices, and we've started to see where we do need to replace those. So as I mentioned earlier on in the presentation, we build and design these systems with a typical 20 to 25 year life cycle or lifetime design in mind, and then with an understanding of what needs to be replaced in the interim. And the DC capacitors are one of those components that we definitely would need to look at replacing, depending on, like I said, the use and the conditions that they are. So that's, and then there are other options. Of course, we continue to improve on the design and capability. There are other types of DC capacitors that are in the market that we are also looking at and looking at how that improves this.
Okay.
Right.
All right. Ian says, great presentation, Arend. I think you should know that. That's thank you, Ian. For Sadi, question is from Sadi. And Sadi had a question that, could you tell us if you have experience with STATCOMs supporting tension, and I think in this case they might be talking about voltage here, in filtering harmonics and mining loads. So do you have experience with supporting the voltage with STATCOMs within the mining environment, and in particular VFD drives, gearless mill drives, those types of drive systems, and the requirements to work at high altitude places, so mines at high altitudes, perhaps in South America?
Yeah, sure. Like I said, one of the things that I mentioned earlier on in terms of the design considerations for the STATCOM, in terms of environmental conditions, I mean, these are designed for up to 1,000 meter without any derating. But beyond that, the derating applies. But what we have to do really is to take into consideration the actual location, and of course it can go as high as what is needed. I mean, other factors that come into play are what's the maximum ambient temperature ranges that would be imposed, design of the insulation levels of the components that we are going to be selecting, and transformers and things like that. All of that will take into consideration. So altitude is really not an issue. I mean, it will affect derating, but it just means that we have to include more capacity to counter for that from that perspective. At the end of the day, it's how many vars is needed is what's going to be needed, and that needs to be provided. With regards to experience on mines, definitely, as I mentioned earlier on, we have active installations in Australia, and we also have installed at mines in Canada, exactly for this purpose of dynamic voltage regulation. And these installations actually use harmonic filter banks to manage power factor correction and the filtering that's required internal to the mine. So it doesn't necessarily have to be active harmonic filtering. I mean, really, it's a question of what's the cost-effective way of doing it. And I think what we found from the experience we have, that it is very, very cost-effective to have passive devices take care of the harmonic filtering, because you need the power factor correction from those large loads anyway, of those large loads. So that's already there. It's just a matter of utilizing it. Those cap banks or anything that you would use for a mine inherently would be detuned or filtered to some extent. So that would address the harmonic issues anyway. But yeah, absolutely. And I think we can, if anybody's interested, we can go detail in some of these applications of how that's managed. But I think those last discussion I had about the hybrid solution where you can actually scale down the steady state rating of the dvar system to just what's the dynamic performance requirement of the system, and then try to manage the steady state power factor correction and a longer term requirement with cap banks. And if you can extend that to harmonic filter banks, well, now you're addressing the problem that you just talked about.
Yeah, so I might add, from our perspective, we supply a lot of filter banks into the mines, in the mine environment, and where gearless mill drives are used, and the harmonics are atrocious. So from an active filtering standpoint, it would not make sense. You would be better off to filter that with passive filters, high pass, C-high pass type filters, notch filters. There was a question about altitude here too, and I'll just comment on that. When you go up in altitude, you have less air. Less air means less cooling. So the STATCOM as well as filter banks need to account for less cooling, and then you have less air for insulation, so you have to go up in BIL. So I think that was another part of Sadi's question. I'll go on to the next question. Is a question for NEPSI, this one. They're asking, does NEPSI supply series capacitor banks, series compensation? And the answer to that question is no. We have been asked in the past to quote that. Our experience with series compensation, and remember NEPSI's 2.4 kV through 38 kV, so we're talking about distribution voltage levels for series compensation. Our experience is that those projects generally do not go anywhere. There is some technology in the bypass spark-over device that must bypass the capacitor, and that can be quite complicated. There's really no off-the-shelf type devices to do that. The sizing of the arresters to bypass that capacitor can be complicated. So NEPSI has not supplied series capacitors in any type of environment, and the demand for such devices is quite low, and that's one of the other reasons. So Kyle had asked a question, could the dvar be used with energy storage systems such as batteries in place of capacitors to supply the facility during a blackout?
Carl, conceptually, I mean, conceptually it can be done, but the dvar Statcom itself is not designed or not designed from controls as well as components and all that functionality perspective to be able to do that. But it is something that overall you could do with a Statcom is extend the controls and make sure that the components are designed for it. But really, at the end of the day, the objective of what are you trying to do? I mean, if it's a blackout situation, it'll be. I guess you'll have to understand as to how much battery or energy storage is needed for that condition and all that. If it's for a short term, it's a different answer. But if it's a longer term blackout condition, it's a different answer. But can you do that? Sure. But dvar Statcom is not designed for that purpose.
Okay, so we're moving on to Kutab. He says, do customers require grid code certification, or not only grid code compliant or functionality for Statcom solutions?
No, look, I spoke with grid code compliance and making sure that certifications or validation has to be done in the context of renewable energy integration, and usually grid codes are there for large plants like that because they are developed by independent power producers, outside people, private parties selling into that, and that's where the most grid code compliance comes in. And it's not really just for the Statcom portion; it's really for the whole plant. Grid code compliance. So every installation of a Statcom doesn't require grid code. There is no standard or there is no requirement per se. At the end of the day, it's really a definition of the problem that we need to solve and making sure that the system is designed, studied, and validated that it will address the problem that it's supposed to be installed for.
And I guess I'll make sure, and I think you've said it, but these are studies that are conducted by AMSC, right? You do have a planning group that does these types of studies, correct?
Yes, absolutely, and I think that's a good point to make here again is that AMSC, because we work with all of the developers and customers around the world, we do have a dedicated team of engineers, planning engineers, a studies group who actually use all of the conventional tools that our colleagues in the industry use, PSSC, PSCAD, EMTDC, PSCAD, as well as Dixelant and all of these other programs, really with the aim of working with our customers so that we can understand the problems, we can define the problems properly, we can make sure that the system, the solutions that we offer are configured appropriately, and also we can allows us to where we actually end up selling equipment is to tune the systems and make sure that the systems work when they're installed. And of course follow up with regards to post-installation validation, things like that. So the group is available. We do help with studies as needed. We do not do consulting work. and I think like Paul, like you guys do for the Harmonics studies and things for the application-based, we do that as well and help out as much as possible. So if there's any requirement for that, we are happy to look at it, investigate, and also kind of, give you the results and let you make a decision on that.
Okay, and they're complex studies. They're dynamic type simulations, right? It's not just standard load flow. It's dynamic simulation too. Is that
Absolutely.
True? Yeah.
It really goes down to the impact of the inverter level. So think about load flow studies to define the capacity that's needed and the impact on the wider grid and things like that. But then once you define all of that, then you have to go to the transient stability mode and the response characteristics, do the tuning and all that on a millisecond basis, and make sure that the design, one, it meets the customer's requirement, but also the impact of the customers and the application on the device that needs to be done. So it's a kind of a two-way, but very detailed. Absolutely, it goes into the transient stability analysis.
So I'm going to increment just a little bit more into this, and then we'll move on to the next question. So, which means that there is a model that must be used within these programs, and I assume that you do have these models developed in these programs to do the dynamic simulations. Is that correct?
Absolutely, we have very, very detailed. I would say something that's very representative of the performance of the dvar Statcom. We've developed this model, tuned it, and also validated it because of all the installations that we've done in the U.S., Canada, here, Australia, UK. These grid codes that we have installed our systems in are very stringent, and they have to be validated. They have to be supported with regards to how the dvar system works. And the models that we have for PSCAD, PSSE, and Dixelant type softwares that we use, these really represent the core control logics and the core control approach of how the dvar system behaves. So, to the extent that our engineers are able to really understand and be comfortable with how the system is going to work when it's put out on the grid. And by the way, these models are available. We're happy to share with them. There are some of these models, such as a PSCAD model, that would require a non-disclosure agreement because of the detailed files that come along with it. But other than that, the PSSE model as well as the Dixelant model, pretty good versions of these models are available, without NDA. In fact, we have worked with Siemens PTI, and a very representative model has just been added onto their library as well, and it is an equipment-specific model for the AMSC dvar Statcom.
Okay, we'll move on to another question. This one's about cost. They're asking the question, what is the cost per kVAR or cost per megavar for the Statcom, and an average cost perhaps minus the EPC cost, minus the installation cost? So looking for basically the cost of the equipment.
Well, yeah, I know we talked about it, and it is it is an important discussion point, and cost is always there as to how much it costs. But it's very important, like I said, to make sure that we concentrate on the application. A cost per megavar sometimes is probably not a true reflection unless we know exactly how many megavars is needed to solve a problem. Why I say that is because a 4 megavar dvar unit, as I mentioned, a steady state 4 megavar dvar unit, which costs the same, whether it's applied for a steady state 4 megavar requirement or is it used for a 12 megavar transient requirement. So that cost per megavar can be a misleading fact from that basis. But just to give you an idea about a cost, I mean, a 4 megavar dvar with a transformer and a control system is somewhere in the range of $700,000 to $750,000, depending on where it's going, what's required, what sort of controls might be required, just as an idea of scalability for that. Now, of course, as more systems are needed, does the cost scale linearly from there? The answer is no. We would like to just help you guys make sure understand what's really required, and then come up with a budgetary or a cost guidance on specific applications.
Okay. Next question is about a comparison between a static VAR compensators and STATCOMs. Other than what are the advantages of a STATCOM when compared to a static VAR compensator, other than the fact that it's got sinusoidal current output?
Yeah, well, I think we covered some of the key technical ones, and I think I'm just going to go back to one of those, which is really the performance. Now, if in terms of requiring a SVC or a STATCOM, you do need for both of them dynamic compensation. They both provide dynamic, so you have a choice of either SVC or STATCOM. But depending on the problem that you're solving and how deep sags that you're really trying to solve the problem for, if it is a deep sag problem, a STATCOM inherently becomes the better choice, or sometimes the only choice to fix it. But if you try to fix it with an SVC, it can be a significantly larger SVC because of the V squared effect of those cap banks that you are using in that case. Because as I mentioned, that the output goes down by the V squared effect. So that's one kind of major difference. Second would be, obviously, as SVCs, you have an issue with harmonic filtering. I mean, you have thyristor switched cap banks as well as thyristor controlled reactors, which inherently has a lot of harmonic impact on at the point where the switching of these is involved. So an SVC would always require some significant harmonic filtering, which not only is a part of the reactive compensation, but then its installation, balance of plant costs as well have to be taken into consideration on that. Whereas a STATCOM, if it's just a STATCOM installed at a location, you don't need all of that level of consideration for harmonics. And we talked about harmonics as how a STATCOM does not change the harmonic impedance of the grid as well.
Okay, so we're moving on to some more questions. There's a couple more. Okay, it's about, so do you think solar farms are a demand center for STATCOMs in a range of 5 to 25 MVAR, considering the fact that PV installations regularly use the capability of the inverter?
Yeah, we do have, actually, we have about 5 installations of dvar system at solar farms. Now, obviously, it depends on the capability of the solar inverters that are being chosen. And of course, it all comes down to cost effectiveness and what makes sense from overall cost of the system, whether you want to gear the inverters towards maximizing the power transfer capability, or do you want to take some of that capacity out and use it for ancillary services, for in this case voltage regulation, things like that. Now we do have an installation of a dvar system at a solar plant in Arizona, where specifically actually the dvar system is there to help mitigate flicker. So if there's a lot of distributed solar plants out in the distribution grid that are large enough and are affecting or could affect the level of flicker that is in the grid, and it's not tolerable by the customers or the utility, the dvar system can be very effectively used to address that. And so, the question also is how large is the solar farm? How spread out are the solar inverters, and what capability can be harnessed for the grid requirements? At the end of the day, it's the performance of the grid that matters. And I think similar to how I talked about the wind farms, it's really how the individual turbines or individual solar inverters can manage or not. And that's the question. And also the ability to have a park controller that can act fast enough overall to help address that.
Okay. A general information question: where is AMSC based, and are the STATCOMs being manufactured in North America or in Asia? So they're looking for where they're manufactured and where's your headquarters.
Yeah, AMSC is based in Ayer, Massachusetts, and U.S. Our factory for the STATCOM units is in Ayer, Massachusetts as well. at our headquarters. And to that point, yes, we make all of our STATCOMs here in the U.S. and we sell them worldwide. The transformers, step-up transformers that we buy, we have qualified suppliers in U.S. here in North America as well as around the world to support that. But STATCOM manufacture is all done here in the U.S.
Okay, so there's a question about the hybrid type STATCOMs, and this is probably directed more at NEPSI. It says, which switchgear is used to operate capacitor stages within a hybrid dynamic compensator? So in the past, what is typically done is NEPSI supplies the metal closed capacitor bank or filter system, and the switching device that's used inside that device will be based upon system voltage and what's best for the project. So the switching device that's chosen is based on NVAR rating, voltage rating, and what's most appropriate for the project. So generally speaking, it's not switchgear, but rather a switching device, and that could be a capacitor switch, a pre-insertion resistive type switching device, a standard breaker with a C2 rating. So there's several different options, but typically it's not switchgear, but rather a switching device, and it's installed within the metal closed system itself. I would guess I should add that the control of that is coming from the Statcom. There's an integration between our system and the AMSC system. They operate together. I don't know if you want to add anything to that, Naren?
No, I think you covered that.
Okay.
Of course, whatever switch you use and all that, we take that into account in the timings and the soft switching requirements that we would do as part of the integration. But yeah, I mean, all of that integration is available.
All right, so we have a question. Are STATCOMs modular basis to support future growth and changes in the grid requirements? So they're looking for modularity and scalability and the ability to expand it in the future.
Exactly, yeah, and I think that's the beauty of a modular system as ours, where you have 4 megawatt building blocks, and you can use that now. Now, of course, 5 years down the road, if you're planning for 10, 15 year kind of a scalability approach, you don't need to install for a 10, 15 year load growth. You can do that, and and then 5 years down the road, review your load growth, and if it still is there, you can certainly expand on it. And now our control system, master controller, I discussed about it, that would easily integrate newer units into that same, or even you can just expand the power module boxes onto the same bus, because everything is similar construction, substation grade construction on the high voltage side.
Okay, that's it for questions, Naren. This was quite a long presentation, but I think quite detailed, and NEPSI really does appreciate you coming on to our Tech Talk session. Statcom certainly is a sister product to a capacitor bank because it's got compensation capabilities, but significantly different. And I think that we really outlaid, or you did, outlaid the differences between a passive and dynamic type devices.
Yeah, no, I think, thank you, Paul, for the invitation, the opportunity to talk about the technology and the applications. And as you mentioned, I think there is, both the products are complementary. I mean, they both have a place in the industry in terms of the solution space for out there. They have, bring different value propositions, and I think they work for the customer. And obviously the fact that we can do hybrid systems, which incorporates both, it's kind of taking the best of both worlds and giving that to the customer. So I think I enjoyed it. I hope that my viewers did, and thank you for the opportunity.
So maybe perhaps I'll put you on the spot. Perhaps we'll have you come back in the future for discussion about flicker, a deep dive into how you control flicker for in-plant type voltage sags, motor starting flicker, arc furnace type applications, and then maybe another one that could be for external cause voltage sags, such as transmission level faults, how you handle controlling the voltage for your customers with sensitive loads. I think there We covered both of those on the surface, but you could get into some calculations, the type of studies that are required, and more specifics on the equipment. So I could see perhaps 2 other tech talks in the future.
Absolutely, absolutely. Would be honored to do that.
Okay, great. Well, thank you for coming on, and we'll wait till next time to see you again.
Thank you, Paul.
Yep.
You're welcome.
Okay, you're welcome. All right, so we're going to next week. We want to make sure that first of all, PDH credits. We're going to go with 2.2 PDH credits. We're actually we're about 2 hours in, so 2.2. So it's quite a bit of time. Make sure you send us an email. We're going to go with that code of 222. So just send us the code 222, and we'll get you a certificate. And then for next week, I want to also tell you we're going to be doing a 2-part series on harmonic analysis, starting with the basics and working up through some more sophisticated systems, how analysis is done, and how to actually understand what the programs are doing. What does Easy Power, ETAP, and SIME, and all the software packages, how are they doing the calculation? And it's our belief that if you can do it on paper, you understand the program. And without being able to do it on paper, you can't understand the program output. So we will build a system from the basics, from the ground up, and it will be a 2-part session. So we won't run quite so long next week. We'll make sure we split it into 2. But it's a great presentation. I've given it many times. So look, I look forward to doing it next week again. So until next week, thank you.